All right, so we're on to lesson 1.8, which is all about inverse functions. So briefly in the last section, we said that if the composite function of, one function being plugged into another and then doing the reverse, both resulted in the same answer, and that answer is x, then we can call those inverse functions. So we're going to talk a little bit about the properties of inverse functions. We're going to talk about the horizontal line test, which tells us whether something has an inverse. And then we'll talk about how to find an inverse or verify that a function is an inverse of another function. So here's a very basic set of inverse functions. Right? We have x plus 2 and x minus 2. You'll notice that in the tables here for the two functions that we have the point 1, 3, let's say, for the first one. Right there. For the second function, notice the point is 3, 1. So one of the properties of inverse functions is that the coordinates, right, for the first function, x1, y1, become the coordinates in reverse for the other function. So the x value is actually the y, and the y value is actually the x for the second function. Okay. So here it says, right, that f of x, let f of x be a function containing the ordered pairs x, y, inverse function, which, by the way, we write f to the -1 of x, right? This means inverse. And be careful, right? This does not mean reciprocal or doesn't represent to the -1 power, right? So that's actually a really bad notation, and I've never liked it, but I wasn't the one that came up with it. So just keep in mind that the f to the -1 really means the inverse function. Okay, so the ordered pairs are x, y, and so for the inverse function, those pairs are yx, which is what I just stated above. To verify the two functions are inverses algebraically, we just need to do f of f inverse and f inverse of f, and both must give us the result x. Another property of inverse functions is that they are reflections of each other over the line y equals x. So if you wanted to do a quick sketch, you could show the line y equals x and then just flip the graph over that line. A function is defined to be 1 to 1 if for each value in the domain there is exactly one value in the range. We can test a function for this property by using the horizontal line test. So every x, there's only one y, and the other way around, right? Because of that, there's only one y for every x. That's 1 to 1. And again, the horizontal line test is how we test for this. So let's look at these examples here. This here, we have f of x equals x cubed plus 1. That's actually this red curve here. Okay, this guy right here is f of x, and this curve right here is g of x. So you'll notice that some of the properties we were mentioning, right? The 0.01 falls on f of x. Inversely, the 0.10 falls on g of x. And then also we have the 0.12, and on g of x, it's 2, 1. So you'll notice, right, that those points are inverted. Another thing you'll notice about the two functions is that if I were to take the function f of x and I were to rotate it or flip it over this blue line here, which is the line y equals x, right? I get the blue line, or the blue curve, I should say. All right. The picture on the right shows us an instance where a function actually fails the horizontal line test. So if we go back to this first example quickly, right, we can do horizontal lines, and there's not going to be perfect. You'll see that this only touches the red curve at one point, right? So we're only looking at one curve at a time, right? Don't confuse this with touching the blue curve as well. So the function x cubed plus 1, in fact, is 1 to 1, and it has an inverse function, which is the cubed root of x minus 1. The example to the right shows a function which is x to the fourth minus x squared minus 1. And drawing a horizontal line, notice it touches the curve in two places. And you can do this anywhere, right, to see it. Right, touches here and here. So for every value of x, there is not just one y, or vice versa. So this doesn't pass the horizontal line test, and therefore no inverse function. Okay. All right, so let's go ahead and take a look at a few of these examples. Graph the following functions on the same Cartesian plane to show that the following functions are inverses geometrically. So I'm going to go ahead and, instead of doing this by hand, which won't look very good, I'm going to go ahead and hop over to Desmos. All right, so I have Desmos here. Let's put in the functions. So I have x divided by 4. Then I also have 4x. Those are my two functions. I'm also going to plot the line y equals x. And I think if we do this, let's make it a dashed line, so we know that that's the line that we're rotating about. Okay. And then I'm also going to plot some points just to prove that this works. Well, first we can do something like y equals 1. Okay. You see that purple line there? That's a horizontal line. Let me just hide one of these for a second, right? This function, for instance, you'll see that that purple line only crosses the red line at one point. So it passes the horizontal line test. Okay. Now let's put in some actual just points. So let's put it in ordered pair. So what's one ordered pair that appears to be on the blue curve? It looks like maybe 1, 4, right? So let's put on the ordered pair 1, 4. And let's make that blue to go along with the curve. And let's put on the, we can go ahead and label that. And let's put on the point 4, 1. Right? If these are to be inverse functions of one another, then that point better lie on the other curve. And in fact, it does. And you can do this with a couple other points. Now let's make this a little bigger here for you, a little easier to see. So these two functions are indeed inverse functions. Okay. Here's another example. We have 1 minus x cubed and the cubed root of 1 minus x. So let's go back over here. And let's put in the new equations. So we have 1 minus x cubed. And then we want the third root. So we're going to do, I believe it was 1 minus x. Let me just double check. 1 minus x. And then third root, I'm going to represent by doing caret 1/3. So 1/3 power means third root. So that one's maybe a little harder to tell. It's get these points out of here, right? We don't need those. So let me just turn this off for a second. Right, 1 minus x cubed looks like this. If I were to put in some horizontal lines, right, we can do this. Just pick some random values, and this only touches the curve at 1 point. It's actually a little hard to tell here, but if you were to zoom in infinitely, this does in fact only touch at 1 point. So if this guy has an inverse, then they're claiming that this is it. And it might be a little hard to tell, right, that this is rotated about this line. Let me go ahead and make that dotted again. Okay. Another thing that we can do is we can put points on the curves. So let's do the ordered pairs that this crosses. Actually, here's a nice one. This is 1, 2. So 1, 2. And then therefore, if the other function is its inverse, 2, 1 should be on that curve. Sorry, negative 1, 2, and then 1 here as well. Okay. And let's just make this match. Okay. So you see that the point here on this curve exists on, opposite on that curve. Okay. And we could pick another point. So let's find another nice one that goes through. Okay, that looks to fall on that curve. And then let's do the inverse of that, which would be 9, negative 2. And that should be green. And you see once again, right, that those do in fact fall on the curves. And therefore, these are inverse functions of one another.